Jai Hind everyone, myself Richa, Assistant Professor in EC Department of AKGEC. Today we will discuss about the pulse modulation, and it is one of the important topic in the unit 4 of KEC. So actually what is the pulse modulation? What is the requirement of pulse modulation? So before that we will study the method of converting your analog signal into digital signal, right? So sampling is basically method to convert your analog signal into digital signals. Actually, analog signal is the continuous signals, and if we want to discretize this signal into time intervals, then we have to perform sampling. So sampling provide a mechanism for representing a continuous time signal by a discrete time signal, and by taking sufficient number of samples so that this original signal can be reconstructed back, and this original signal can be completely expressed in form of sample. So actually sampling can be done in that form that reconstruction of the signal will be okay. So it can be stated as a band limited signal of finite energy with no frequency component higher than the FM hertz is completely described by its sample values, which are at the uniform interval less than equal to 1/2 FM. It means any signal which is band limited between minus FM to FM. It means no frequency component is greater than this FM, and it can be completely described with the form of sample, and this sample interval, if we will write that the interval is less than or equal to 1 upon twice of FM. Or this can be written as the sampling time can be written as Fs is equal to 1 upon twice of Fm. Here Fm is the frequency of your message signal. Or it can find out sampling frequency must be equal to or greater than 2 FM hertz, or I can write Fs is the sampling frequency should be greater than equal to twice of FM. A continuous time signal may be completely represented in samples and recovered back only and only if your sampling frequency is greater than and equal to twice of FM. Otherwise, signal cannot be recovered back. Where Fs is the sampling frequency and Fm is the maximum frequency component of the message signals. So how it can be done? So sampling theorem we show that the signal whose spectrum is band limited to FM hertz, it can be reconstructed exactly without any error if the samples taken at a regular interval of Fs is greater than twice of Fm. So let us continue. We are taking a continuous signal of xt whose spectrum is band limited. It means spectrum is with minus FM to FM. This means that the signal xt has no frequency component beyond the frequency of FM hertz. Therefore, if we take the frequency domain, then x omega has no frequency component beyond FM hertz. So how it can be performed? First, sampling of the input signal xt can be obtained by multiplying the message signal with an impulse train of delta t, and the sampling period or time period between the samples are Ts. So output of that multiplier is now discrete signal, which we call the sampled signal, and it can be written as yt is equal to xt into delta t. Delta t is nothing, that is the impulse train. So Fourier representation of this delta t, we can Fourier series representation is a naught plus n varies from 1 to infinity an cos n omega st plus bn sin n omega st, right? So this expression we will use. So how it will be performed? See here, this is the message signal, right? Message signal xt, and this is train of pulse with a time gap of Ts, right? These two are given to one multiplier, and output of multiplier is this one. Both will be multiplied. This is the time domain representation. When we are going to frequency domain, this xt will be right like this, with a frequency of your, I will write omega m and minus omega m. And frequency representation of this is y omega, this is 0s, right? And we can say that fs should be greater than equal to twice of fm, then only your signal will be reconstructed back. So proof, see here, this is your train of pulse. Here second term is 0 because we are using the delta pulse. So 1 by Ts minus 1 to infinity 2 by Ts cos of n omega st, right? So this equation we are using to find out our sampled signal. So we will use this in equation 1. What is your equation 1? Is xt is equal to xt into delta t. So xt will be multiplied with delta t. So here xt into delta t 1 upon ts plus n varies from 1 to infinity 2 by ts cos n omega st 0. This is the multiplication. So when we will do the multiplication, 1 by ts we can take an outside, and it is xt plus twice of n is equal to 1 to infinity cos of n omega st into xt. So like this. So this is your equation. This is in terms of time domain only, right? So if we are using in time domain, so it comes out to 1 upon 2, 1 upon ts xt. So this is a summation from n is equal to 1 to infinity. If we open this summation, we can write twice of cos omega st xt plus now n is equal to 2, twice of cos 2 omega st xt, now n is equal to 3 plus twice of this. So when we take the Fourier transform of these terms, so as we know, the Fourier transform of xt is equal to x omega, right? Fourier transform of 2 of cos omega st is equal to x of omega plus omega s plus x of omega minus omega s. In the similar way, your twice of cos of 2 omega st Fourier transform will be x of omega plus 2 omega x plus x of omega minus omega x. Okay. So in this way, we can replace this time domain signal with the frequency domain, and the final expression comes out to be 1 upon ts x omega plus x omega minus omega x. So this is for, these two terms are for twice of cos omega x, and this is for twice of cos 2 omega x and further on. So finally, last equation is a summation of these two when n varies from 1 to infinity. So I can write j omega is equal to 1 upon t. It varies from minus infinity to infinity x of omega minus n of omega x. So if you want to reconstruct, this is your sampled signal. I can write sampled signal. If you want to get sampled signal back, reconstruct, if you want to our original signal back, so what we have to do to reconstruct xt, one has to recover input signal from x omega, because xt is your original signal, Fourier transform was x omega, so we have to recover our xt from x omega, and this x omega is recovered from output signal of x y omega, right? So sampled signal spectrum y omega, which is possible when there is no overlapping of the samples between. It means if each cycle is not overlapped, then only it will be possible to recover the signal. So it can be happen in the case of when your sampling frequency is greater than equal to twice of fm. So this is the case when your sampling frequency is greater than or equal to twice of FM. So these cycles, sample cycles are not overlap. There is a gap between two samples. When your Fs is equal to twice of Fm, we can say it is a perfect sampling. There is no overlapping, but it is touching with each other. When your sampling interval, sampling frequency is less than twice of message frequency, so here is the overlapping of the signal. This overlapping, if overlapping of the signal is there, then your signal cannot be reconstructed back. So because of the reconstruction, the minimum requirement for a sampling frequency, it should be equal to twice of Fm. What is that? Fm? Fm is basically, twice of Fm basically is the bandwidth. Because your signal is band limited, if I am dealing with one signal, the signal is band limited between Fm to minus of Fm. So bandwidth will be twice of Fm. It means if you want to sample any signal, then the sampling frequency should be equal to or greater than the bandwidth of that signal. In terms of your Nyquist rate, so minimum sampling rate is Fs is equal to twice of Fm. It is not known as the Nyquist rate, and the Nyquist interval is equal to Ts is equal to 1 upon twice of Fm. So when your signals are overlapped, so this type of effect is known as the aliasing effect. Aliasing, it means overlapped region in case of undersampling. Why it is called undersampling? This is the perfect sampling. When your Fs is greater than 2 Fm, it is called oversampling, and when your Fs is less than 2 Fm, then it is called undersampling. In case of undersampling only, the samples are overlapped. So it can be termed as the phenomena of a high frequency component in spectrum of a signal taking on the identity of a lower frequency component in the spectrum of its sampled version. See here, what is the meaning of this statement? If I want to draw a signal, this is the frequency axis, I am drawing a signal here, and if next signal is this one, if next signal is this, so this is perfect sampling. But in case of undersampling, this will come here. So we can say this higher component of frequency will lie into the lower frequency spectrum. So this is a type of error which we do not require in our communication system. So it should be nullified. So this effect can be removed by two methods. One method is, if we consider the sampling frequency is always greater than or equal to twice of Fm, then this type of overlapping will not happen. And if this overlapping will be happen, so we will use a anti-aliasing filter. Anti-aliasing filter is a type of low pass filter which will be used to eliminate high frequency component. So these are the two methods through which this aliasing effect can be minimized. So there are three types of sampling. First is the impulse sampling, the natural sampling, and last one is the flat top sampling. So first we will discuss about the impulse sampling. Impulse sampling, it means your message signal is multiplied with the impulse train. So see here, this is your message signal and it is multiplied with the train of pulse with the sampling time interval of Ts. When it is multiplied, we are getting this sampled signal. This is the ideal type of sampling. This is not practical because practically it is not possible to generate a signal of width 0. We cannot generate a signal, right? So practically each impulse is having some value. So ideally we are considering it as a 0 pulse, right? If the width of the pulse is very small, so it will not taken any frequency component. So we will not use this type of sampling here. Practically it is not possible. Next type of sampling is the natural sampling. Natural sampling, it means your signal is multiplied with the train of rectangular pulse, which is having a width of tau. Tau width rectangular pulse is multiplied with your message signal, and at the output you are getting this type of signal. This is a sampled version of the signal. And how it can be generated? It can be generated by a simple circuit in which we are using one switch. Here we are giving our input signal. If your switch is closed, the same signal will be appearing here for a time interval for which your switch is closed. When your switch is open, output will be 0. So for this time interval, switch is on. So this signal will directly come at the output with the same shape. For this time duration, your switch is closed and output is 0. Again switch is on for this time duration. So this signal will come at your output with the same shape. In this way, you are getting natural sample. So this type of sampling is similar to ideal sampling, except that for the fact that instead of delta function, here we are using rectangular train of period Ts, and it is multiplied with your input signal of xt. For this, we are using one electronic switch which is used to periodically shift between two contacts at a rate of sampling interval, that is Fs is equal to 1 upon Tl. It means it will be on and off for the same time duration, that is Ts time duration, and staying on the input contact for C seconds and on the grounded contact for the remainder of the same time. So output xst of the samples consists of a segment of xt, and hence x of xt can be considered as a product of input signal with train of pulses. So this is the clear diagram of your natural sampling input signal xt, the rectangular train pulse with a pulse width is tau, and the sampling interval is Ts. For a particular time duration, your switch is on, this is your signal, then 0, then signal, like this. So in this way, we will draw our signal. So if we see, the shape of your signal is same as the shape of your message signal. The top of the pulses are as the shape of your input signal. So we can say the top of the pulses are continuous in nature. So it can be mathematically represented by using Fourier series. So message signal represent your train of pulses is represent xt is equal to c naught, n varies from 1 to infinity to c cos n omega ct, where the c naught is the time coefficient, that is tau by t, and cn is equal to fs tau sin n fst. So your xt will be, we will multiply it with your xt, s is equal to xt dot st, that is the rectangular pulse. We will multiply message signal with the rectangular pulse. So we get c naught xt plus 2 c1 xt cos omega ct plus 2 c2 xt cos 2 omega xt. So here we were using apply Fourier transform to the above equation. Fourier transform meaning we are converting time domain to the frequency domain in the similar fashion which we have done in the previous slides. So xt Fourier transform was x of f. Xt cos 2 pi f naught will be 1 by 2 x f minus f naught plus x plus f naught for x of st. So in this way we will write, for first case we will write c naught xf plus c1 x minus f naught plus x plus f naught. For second term, c2 x minus f naught plus x f plus f naught. So it means this is a addition of these two terms from minus infinity to infinity. So for simplification, we can write c naught xf is equal to summation n is equal to minus infinity to infinity cn x of f minus n fs. So further it can be simplified. In place of c naught, we can write a tau upon ts, because your c naught is equal to tau upon a, tau upon t. Summation sin c n fs tau x n minus n fs. So signal xt has a spectrum which consists of a message spectrum and repetition of message spectrum periodically with the in the frequency domain with the width of fs. So, but the message term is scaled by C naught. Actual message is now multiplied with one factor, that is C naught, sinc function, which is not the case in instantaneous sampling, right. So, third one is the flat top, because what is the reason we are going to the flat top? In the natural sampling, sampled signal will, the top of the sample signals are the same as your continuous manner. So, this will be affected by the noise. To remove the noise component into the sampled version, we are going towards the flat top sampling. So, during the transmission, noise is introduced at the top of the transmission pulses, which can be easily removed if the pulse is in the form of flat top. It means in the natural sampling, your tops are like this, and if we can remove and make the pulses like this, then noise effect will be less. Here the top of the samples are flat, that is they are constant amplitude and is equal to the instantaneous value of the baseband signal, and this is at the start of the sampling. So, that is why it is called flat top sampling or practical sampling. Flat top sampling makes use of a sample and hold circuit. It means switch will be closed and it will hold the output till the time again the switch is open. So, in this way your sample and hold circuit will be used to find out flat top sampling. The sampled signal can be obtained by convolution of rectangular pulse HT with ideal sampled signal of ST. So, your output will be GT is equal to ST into HT. So, after sampling we will discuss the pulse modulation. So, pulse modulation is basically divided into two parts. One is the pulse and analog modulation, and next is the pulse digital modulation, right. So, pulse amplitude modulations, in this category three type of modulation comes in this category. First is the PAM, full form of PAM is the pulse amplitude modulation. Next one is the pulse width modulation. Third one is the pulse position modulation. So, I can write it here, pulse amplitude modulation. Next is the pulse width modulation. Third one is the pulse position modulation. In the category of pulse digital modulation, first is the pulse code modulation. Next is the differential pulse code modulation. Third one is the delta modulation, and ADM is the adaptive delta modulation. Analog modulation means your signal is analog. You are modulating analog signal by using pulses. It means carrier are in the form of pulses and input signal is in the form of analog. Analog signal is converted into the form of pulse using carrier pulse. So, first type of carrier pulse modulation is the pulse amplitude modulation, which is called PAM, right. As per our amplitude modulation, in the amplitude modulation, amplitude of the carrier is going to change. Here amplitude of the pulses, what is pulse here? Pulse is carrier here. It means here we are using carrier as a pulse train. Now, the amplitude of this pulse train is going to change as per your baseband signal. So, amplitude of the pulse carrier varies proportional to the instantaneous amplitude of the message signal. So, here if we are dealing with the pulse, right. So, this is the pulse train. Again there are three quantity which can vary in pulse. First is the amplitude, second one is the width, and third one is the position. So, in case of amplitude modulation, width and position we are taking constant. We are only playing with the amplitude of the pulse. So, pulse modulation can be of two types. First is the single polarity pulse and PAM. Next one is the double polarity PAM. Single polarity, it means signal is positive side. A suitable fixed DC bias is added to the signal to ensure that all pulses are positive. In the double polarity, in this the pulses are both positive and negative. So flat top PAM, see here, this is the waveform. If we draw the top of the waveform, this will be your analog signal, unipolar. Bipolar, it means these are your pulses, and if we draw, it means it is positive and negative. So this will be your bipolar signal. So pulse amplitude modulation, amplitude of this pulses. So this is your carrier. Carrier is in the form of pulse. So amplitude of these pulses train is varied in accordance with the modulating signal. That is, amplitude of pulse depends on the value of MT during the time. It means at this time duration, what is the amplitude of your message signal? And it is taking the lower value of the amplitude, right? So this lower value. At this time interval, what is the value of your message signal? This one. So in this way, we will convert our message signal into pulse amplitude signal. So how it can be done? In fact, the pulses in a PAM signal may of flat top type, natural type or ideal type, any type, but we prefer flat top. Flat top PAM is most popular and it is widely used. The reason for using flat top PAM is that during the transmission, the noise interference with the top of the transmitted pulses, and the noise can be easily removed if the PAM pulses as flat top. If we are using natural PAM, in natural samples PAM, the pulses has varying top in accordance with the signal variation. Such type of pulse is received at the receiver and it is always contaminated with the noise. So to remove the noise, we are going towards the flat top. Then it becomes quite difficult to determine the shape of the top of the pulse, and thus amplitude detection of the pulse is not exact. So generation of PAM, as we know, there are two operations involved in the generation of PAM. First one, instantaneous sampling of the message signal MT at every Ts second, where the sampling rate is equal to 1 upon Ts is to be chosen in accordance with the sampling theorem. Second one, lengthening the duration of each sample. So this sample duration we can increase, so obtain constant value of T. So this is nothing, that is the PAM waveform. So this is a circuit of a PAM. How to generate a PAM? Here we are using two transistors. These transistors will act as a switch here. First is the sampling switch, second one is the discharging switch. Here we are giving our input signal. Input signal is xt. This switch G1 and G2 will be on and off. G1 will be on for the time duration for which we want signal at the output side. If this switch G1 is on, it means the same signal coming here and it will charge the capacitor up to the maximum value of your message signal, and output will be as per voltage across C. So this waveform will comes here. When this capacitor will be charged to fully value, then this switch will be open and this switch will be closed. Now when this switch is closed, capacitor start discharging from G, this transistor G2, and it comes to the value of 0. And at that time we remove this circuit also. So voltage across capacitor will be output, that will be 0. So this type of waveform we will receive here. So mathematically we can say this is your delta T pulse train. It will be multiplied with your message signal. Convolution of these two, we are getting our output waveform. So mathematically we can express the same. The train of pulses, this train of pulses will be multiplied with the message signal. So we are getting this xt. Now this xt will be convoluted with our ht. ht will be convoluted with this xt. So we are getting our final expression, that is gt. So frequency domain, if we are taking the frequency domain, g of f is equal to sf into hf. So this can be written. So by using the shifting property, So this is the ft delta t minus t naught, we can write f of t naught. So this shifting property we are applying it here. So we are getting from this shifting property, this factor remain the same, and this shifting property, it means f of t naught, it means f can h of t naught. This is your t naught, t minus nts. So this is your final expression for spectrum of flat top samples. So transmission bandwidth, it means PAM signal, the train pulse duration is tau and it is assumed to be very small as compared to time period of Ts. Tau is less than Ts. So maximum frequency in the modulating signal xt, and it should be, Fs should be greater than equal to twice of Fm, and Ts should be less than 1 upon 2f. So this Ts lies between tau and 1 upon 2 of Fm. So maximum bandwidth is greater than equal to 1 upon 2 tau, because it is on for tau 2 duration. So it is 1 by 2 of tau. Here 1 by tau plus tau, it comes out to be 1 by 2 tau. So these are some transmission of PAM. PAM signals to be transmitted through space using antenna. They must be amplitude, frequency, phase modulated by high frequency carrier, and only then they can be transmitted. So this overall system is PAM AM. PAM FM or PAM PM at the receiving end. AM FM PM detection is first employed to get PAM signals, and then message signal is recovered. There are some drawback of PAM also. Bandwidth required for the transmission of PAM is very large in comparison to the maximum frequency present in the modulating signal. So since amplitude of PAM pulses varies in accordance with the modulating signal, so interference of noise is maximum in PAM. Next, variation of peak power required by the transmitter. So these is all about your pulse modulation, particular pulse amplitude modulation. Jai Hind.